Hi, welcome to part 3. In this part, we'll continue with the functions. In this part of functions, we'll study odd and even functions, and also we'll try to understand how they are different from the previous functions and why understanding these functions is important. Also in this part, we'll look at inverse of the functions as well as periodic functions and its modern interpretations. So stay tuned for part 3. Let's move on to the lecture part. Now, let's come to the next part where we study odd and even functions, which can also be defined as an inverse of the function. Now, in this part, it has two different subtopics. One, obviously, the odd and even function. Then the other is how we study inverse of the function. Okay. Now, let's start off with odd and even function. Now, the odd and even function, for that I have, if my function f for x to y is a real valued function such that the value of the x belongs in the domain and also the negative of that value is also belonging in the domain, then f of minus x gives me f of x. Okay, for every x belongs in D, then f is said to be an even function. Okay, and if f of minus x gives me minus of fx, then f is said to be an odd function. Okay, so basically the negative value of the function, if it gives me a positive function, then it is an even function, and if the negative value of function gives me a negative function, it becomes an odd. Alright, now let's look at the facts based on that. Now, the even functions, they are symmetrical about the y-axis. Okay, that is, if I draw it in the graph, it will be something like this, symmetrical about the y-axis. That is, xy lies on the curve, then minus xy also lies on the curve. Okay, odd functions are symmetrical about the origin, and it is placed either in the first quadrant or in the third quadrant or in the second quadrant and fourth quadrant. So basically it will have the combination of 1 and 3 and 2 and 4. Okay, so if xy lies in the curve, then minus x minus y will also lie in the curve. Okay, now my function fx is set to be 0 is the only function which is both even as well as odd. Why so? That is, for this case, you see, this will satisfy both the criteria, okay, of being in this one also and maybe something like this. Alright, so basically fx equals to 0 is the only function where it is both even as well as odd. Now, a function is an odd function. If a function is an odd, then fx is an odd function only, that is provided if function it is differentiable on R. Now, for this case, we will have to study differentiability and continuity. You will learn more about it in that topic, but this is just a fact that you need to remember. Okay, so basically, if my odd function exists something maybe like this, then it has to be differentiable. Okay, that is, it has a gradient, which most cases it does. Alright, now if based on the odd and even function I have, my fx will be equal to f of x plus f of minus x by 2 plus f of x minus f of minus x by 2. So this will give me f of x plus f of minus x is an even function, and f of x plus f of minus x by 2, it becomes an odd function. Therefore, x is 0 and it belongs in the domain of f. Then for odd functions fx, my f of 0 is 0. That is, for a function f not 0 is equals to 0, then the function cannot be odd. Okay, now let's come to the inverse of the elements, that is the inverse of a function. What does that basically mean? If I have a function f a to b be the function from A to B, then for any A belonging in A, if f of A is equals to B, then A is said to be the pre-image of B. Okay. Now, basically, if I have my f of A is B, so basically what does this signify? This is the pre-image of the function. So the function, it exists but it already has a domain, okay, or its codomain or its range. Okay, so there has to be a pre-image of B on the inverse of B, denoted as f inverse of B. Okay, so it has to be like this. You see, A1, A2 has an image over here, and B already has a pre-image from these two. For this also, you see, two cases. Thus, if for A to B it is given, then the inverse of any element may be unique, may not be unique. Okay, inverse of any element may not be unique. Okay, because you see, if I look at the pre-image of this, it will be either this or this. So there is no unique value. Alright. So for every case, such cases, I need to find out the inverse of the element. It may not be the unique value. Now, in that case, if I write f inverse of B1, will be A1 and A2, and f inverse of B2 will be A3 and A2, and f inverse of B3, it is null. Okay, now you see, in all the three cases it is not a unique value. Okay, now let's say if I have a function A to B, it is an objective function, then we can define a new function from B to A. Basically, if I reverse it like this, it can be denoted as like f of inverse B to A, given by f inverse B is equals to A, and if f inverse A equals to B for all B belonging in this element. The element obviously has to exist. That is, each element of B is associated or mapped to its pre-image under the f of the given function. Okay, so it is like this. You see, my A is equal to f inverse of B, and my f of A is equals to B. So it is like this, and the f inverse function, it goes from this direction to this direction. This becomes the function and this becomes the answer. Now, how do I find f inverse? It is a very interesting part. Okay, first of all, I need to know that for a function f A to B, if it is an objective function, then f inverse can be obtained using the following steps. First of all, I let the function be something in terms of y is equals to fx, then express x in terms of y, then say x is equals to g of y. Everything I interchange from x to y. Interchanging x with y, that is, x will be as equivalent to y, we get y is equals to gx, right? For some function, it was y equals to fx, so I came on to y is equals to gx, then g is equal to the f inverse. Now this new function g will be the f of that. Now I need to note that in this cases, before finding f inverse, you have to prove that it has to be a bijective function. So it has to be bijective function. Alright, that is 1 1 as well as an onto by using the rules. You need to first find out by the rule that it is a 1 1 and onto, then only you can find the inverse of that element. Okay, now the properties for this inverse function says that the function is irrevertible if it is bijective. Inverse of bijection is always unique. Inverse of bijection is also a bijection. If f of A to B is bijection, then f inverse of f is an identity. Similarly, this one, f of f inverse is also an identity. You can understand that logically, where IA and IB are the identity functions and A and B respectively. That is, f inverse of f is equal of A is A, f inverse of f f of f inverse b is b. Okay, for all a and b. Now the corollary of that says that if for any function from a to a is bijection, then f of f inverse is equal to f inverse of f, which is equal to ia. If my a to b and g b to c are two bijections, then the inverse of g of f for a to c is also given to be in the same order of g of f. G of f inverse is equal to f inverse of g of inverse. Okay. Similarly, I can have, if any, for any function a to b and b to a, two functions such that a to b and b to c, then f and g are bijections and g is the equal to f inverse. Now in this case, the domain is equal to range of the function inverse or the f inverse, and the range becomes the domain of f inverse. Now that was all about the inverse function. Next we come to the final part of a function, which is just a theoretical concept of periodic functions. Now this periodic function, the name itself suggests how the characteristic sticks. Okay, the characteristic for this case sticks in a way like, you must have seen heartbeats like this. Okay, going like this, going like this. In movies we see, right, the heartbeats going like. Now all of this, they are all in periods, right, and they are same in during this period, right. This, if I write the function for this case, it becomes a periodic function. Okay, so basically a periodic function is a function that repeats its values in regular intervals or periods. The most important examples are the trigonometric functions, which repeat over intervals of 2 pi radians. Okay, that is, for any fx is equal to fx plus mp for all x and any integer of m. So basically periodic function, they, like if we look at the curve of a sine, you see 0, pi, 2 pi, right. Then again after 2 pi it repeats like this. Over here it is 4 pi, then again it will go like this. You see, so this is the best example for a periodic function. Now let's have a look at the questions based on the topic that we have just discussed. Okay, now this question here says, if the function f and g are defined from the set of real numbers r to r such that fx is equals to e to the power x and gx equals to 3x minus 2, then find the functions f of g and g of f. Also over here I have to find f of g inverse and g of f inverse. How do we do it? We start with the first part. We start by finding f of g and g of f. What do? We know that f of g x equals to f g x, right? So it becomes f of 3x minus 2, which gives me e to the power 3x minus 2. Next, g of f is equals to g of x, which gives me g of e to the power x, which gives me 3 e to the power x minus 2. Okay, next comes, first we need to find, so this is my f of g and this is my g of f. To find f of g inverse, we let y is equals to 3x minus 2. We see we will follow the 3-step process that we have studied, right? So we will let y is equals to 3x minus 2, then it becomes, we solve using the log here, right? 3x minus 2, then it becomes log ey, which we solve, it gives me x is equals to log ey plus 2 by 3. Therefore for x is equal to or equivalent to y, we get f of g inverse is equals to log e to the power x, log ex plus 2 by 3. Now I need to find g of f inverse. For that I let 3 e to the power x minus 2. Then the same process I follow here, and I get my g of f inverse is equals to log e to the power log e x plus 2 by 3. In the next question we have, if fx is equals to sine square x plus sine square x plus pi by 3 plus cos x into cos x plus pi by 3 and g 5 by 4 is equals to 1, then I need to find g of f. Okay, I have 4 options over here. How do we solve it? Same process. I take g of x. My g of x gives me, as gx is defined by x equals to 5%, we cannot find g of x in general until we find fx turns out to be 5 by 4 for all x. So we simplify fx. Simplifying fx gives me this form. Now this form is a little lengthy, so I need to shorten it further. So I keep solving it till I get a simplified figure, and my final answer comes out to be 5 by 4. Why? If you solve this, if you have a look at this, I get it in the form of sine square x plus cos square x. Everything else is self-cancelable. Okay, so now I have my final value to be 5 by 4. So that is satisfied. So my g f x is equals to g 5 by 4 is equals to 1. That is satisfied. Thus I have the answer to be A. So my answer is equals to 1 for g of fx. Now let's move on. In the next question it says that if f is 1, 2, 3 and so on, which belongs to from that to 0 plus minus 1 in this form continuing, it is defined by y is equals to fx for the given condition, then f inverse of 100 is equals to what? These are the 4 options. Again we follow the same procedure of solving. For f inverse of 100 I let that be equal to x. So I have my fx is equals to 100. Now x is even, then fx is equals to x by 2, which is equals to 100. So that will give me x is equals to 200, which belongs in the given set, right? Now if x is odd, then also I'll have this kind of an equation. My fx is equals to like this. In that case also I will have a situation where it belongs in the given condition, but for this case the value of x does not satisfy the given domain, that is the positive real numbers. Therefore f inverse of 100 is equals to 200 and not this. Okay, so that is my answer over here will be D. Now coming to the next question, this is the final question. I have, if for a function from 0 to undefined to real such that my fx is equals to log 3x, then I need to find f inverse of x. Now in this part we'll try a little different method. First I have my y is equals to log 3 log base 3x, base is greater than 1, then the domain I have is given from 0 to undefined. So my codomain will be equal to R, then the range is equal to R, which becomes my codomain, which is actually my codomain. Then in that case it becomes an onto function, right? My codomain and range, they are same. My domain is from 0 to undefined, so the function becomes an onto function. So I will let my fx is equals to fy. Then from that I can get my x to be equal to y. Why? Because log 3x is equals to log 3y, so the antilog of this one, if this log comes this side, it becomes an antilog, so I'll get my x is equals to y. Therefore my function f is 1, 1. So f inverse of x does exist. Okay, so now we'll take our first step. Let y is equals to log base 3x. Step 2 will give me x is equals to 3y. Then I have for x to y, we get that y is equals to 3 to the power x. So f inverse of x is equals to 3x. Therefore, so my f inverse of x is equals to 3 to the power x. And for this, I have my solution. Okay. So that is all in this topic. Okay. I hope you have understood everything. Just keep following.
With this, we have come to the end of part 3, and also we have come to the end of the part of functions. So this is all that we have in our topic called functions. In this part, you studied odd and even functions. We introduced to you inverse of the functions. Also, you came to understand what periodic functions are. Moving on to the next part, in part 4, you will see the next topic, which is logarithm. Logarithms are modern day mathematics. It is an extended form of exponents. When exponents became complicated, logarithms were introduced to simplify those forms. So stay tuned for part 4.